Okay, any questions about the quiz? We will almost finish the material today, but there'll be some stuff tomorrow that will mark the end of the coverage of the new material, and then we'll do the review like we did last time. Now, I'd like to start off with an analogy to help you maybe to understand or conceptualize what's going on with all these energy work concepts that we have. I was actually, last time I avoided making this analogy, but then I thought about it more this weekend, and I realized for some people this is actually very helpful. So I'll give it to you. If it doesn't help you, you can just put it aside, okay? So here's the analogy. All right, we're going to think of energy, and we're going to make a connection with something we all know and like, money. Okay. So if we think of energy as making an analogy with money, then kinetic energy, I like to think of kinetic energy is cash on hand. How much you have in your pocket right now. So that's like kinetic energy is the energy associated with something that's moving. And so if you're moving, you think that you're traveling, you're going somewhere. It's how much energy you have in your pocket. Okay. So now if kinetic energy is cash on hand, then potential energy for a conservative force. So remember, a conservative force is one where the work done doesn't depend on how you go from the initial point to the final point. All the paths give the same amount of work. So then we can define a potential energy. We did that for gravity. We did that for the elastic spring force. Remember this guy? Okay. So those two cases. And this corresponds with money in a bank account. Somebody is taking care of the books and tells you how much money you have in the bank account. Okay? I'll come back to these in just a moment. And now let's make some more analogies. So then work will be like the transfer of money, either a deposit or withdrawal. Okay. Now, if I think about positive, okay, thank you. Positive work by a conservative force. That will correspond with a withdrawal from the bank. You tap some of that that bank account, that potential energy, you tap some of it out, and you take a withdrawal from the bank. Now, if the conservative force is doing negative work, by a conservative force, should have written force here as well. This is a deposit into a bank. Okay, so these analogies make some things rather easy to understand, or at least conceptually kind of easy to understand. So let's consider we have an isolated system, and we have here we have our kinetic energy, which is like our, as I said, the cash on hand, and then we have, so kinetic energy is like the cash on hand, and then we have the potential energy. Right? So now, remember we said that the total mechanical energy, the sum of K plus U, that's equal to the total mechanical energy, and this thing is conserved for an isolated system. All right? Everybody's with me on that? Remember? We said K plus U is the total mechanical energy, and that if it's an isolated system, that's not changing with time. So I just think about the money I have on hand and the money I have in my bank account. If I add them together, and there's nothing else affecting me, so it's an isolated system, so I'm not talking to anybody else. I just have my bank account and I have my cash in hand. If I add up the money I have cash in hand plus the money in my bank account, it's not changing. Does that make sense? Okay. We're not putting all these complications like interest in the bank account. Okay, you have one of these cheap bank accounts that don't give you any interest. So just think of it that way. So then, whatever the potential energy gives to the kinetic energy or vice versa, it doesn't matter to the total. It's being transferred from one to the other. And that's essentially what's going on here. Okay? So here, all the money went out. So kinetic energy is the money on cash in hand. All of that energy is in motion. Okay? Whereas when the ball is up here, it's all stored in the bank account. So it's basically, it's going back and forth. The money starts in the bank account, it gets transferred, and you take it all out of the bank, and then you decide, that was such a good idea, I'm going to put it back into the bank, that's all back into the bank. Then you take it out again, and it goes back and forth like that. Okay? Does that make sense, everybody? So you're just transferring it from the bank to your pocket, to the bank, to your pocket, and so on. So for me, that helps to visualize what's going on with energy. It's kind of like money sent back and forth. Now, the point about positive work by conservative force is like withdrawal from the bank. Remember I said that, let's think about gravity. It's a conservative force. Okay? It's trying to push things down. Right? But when I lift my calculator up, is it doing positive or negative work? Yeah, it's doing negative work. Remember, it's like a pushing match. I'm winning, and I'm pushing, and gravity is losing. Right? It's trying to push this way, but it's moving upwards. So when I go from here to here, gravity is doing negative work, but because it's doing negative work, it's sort of like storing up that energy into its bank account. Does that make sense to everybody? That's why I'm saying that when I have negative work by a conservative force, it's like a deposit into that bank account. So it's storing up that energy, and then it can let it go and do something with it. Okay? Similarly, if the conservative force is doing positive work, if I'm from here and letting it go down, then what I'm doing is I'm taking stuff out of the bank account and it's doing positive work as a result. Does that make sense to everybody? Okay? So up here, it's got a lot of things stored, but now it's going to spend some of that money and it's going to push things down. It's going to do positive work. It's going to go down. Okay. Any questions? Pretty good? Okay, then I can make this concept very clearly. All right. And this equation, which is sometimes confusing to people. So, oh yeah, I have this picture of the picture of money here. Okay, so here's the conceptual picture. So this is like a bank, and this is the potential energy, which we call U. And we have all this energy, which is like money. Okay, and let's say we take some out. That means it's doing work. Okay, and so we are withdrawing some money here. And so this is the work done by this particular conservative force. Right? And the point I want to make is for any conservative force, the change in the potential energy, how much change is in this bank account will be equal to negative the work done by that force. Okay? Does everybody understand the minus sign? Right? If you take money out of the bank, take $100 out of the bank, you're taking positive money out. Your cash on hand, okay? You're taking money out. So the potential energy, the conservative force is doing positive work. Okay? But if it's doing positive work, it has to lose some of its potential energy. Does that make sense? It has to give something up in order to do it. So this is the easiest way I can explain this minus sign. If you're taking money out of the bank, that's doing positive work, but then your bank account will decrease. All right, that's pretty straightforward, I think. Any questions? All right. Now let's, by the way, did everybody get an email from me on something? There was a mistake with one of the problems? Okay, it was actually this minus sign that was wrong on one of part B of question number 2 for the homework due on Wednesday. So just take a look at that email when you do the pre-class reading for Wednesday. All right, so now what we're going to do is we're going to start talking about forces that are not conservative. So friction is an example. All right, so if we measure very carefully the height of position of this ball, we won't go quite as far up with each pass. So we're actually losing some mechanical energy. Right? It's going into friction, it's going into sound, it's going into a little bit of heat, all sorts of things. And so we're going to talk about what these things are. So last time we said, for an isolated system, with only conservative forces, we said that the change in the mechanical energy is equal to 0. It doesn't change. Okay? Basically saying the initial is equal to the final. So E initial is equal to E final. I dropped the MEC because it kind of gets in the way. MEC is for mechanical. All right, what we're going to do now is we're going to let friction be part of the game. So now suppose now there is a non-conservative force. Okay, what are some examples? For example, you might be pushing or pulling. On an object. Okay? Or friction might be opposing some sliding motion. Okay, it doesn't matter. So we will call these non-conservative forces, and we will say let W work. Okay, so let WNC be, so NC stands for non-conservative. The total work done by all non-conservative forces, everything else. Okay, then the generalization of the conservation of mechanical energy will be very simple. Then we have the following. Then we have that the change in the mechanical energy, so this is change in mechanical energy, remember mechanical energy is this kinetic plus the potential energy for the conservative forces, is equal to the work done by the non-conservative force. total work done by non-conservative forces. Okay. Now, if you want to make an analogy of the non-conservative force and the work it does, the non-conservative force is sort of like a shady bank that doesn't keep track of its books. Okay? That it'll take money out. Well, typically it only takes money out, okay? And it doesn't tell you how much it has because it's longer than it's got. Okay? So it's kind of like that. Friction takes the energy out, but you don't really know. Well, it's hard to figure out exactly where it went. It did go somewhere, but it went into heat. It went into raising of the temperature of this track. Some of it went to raising the temperature of the air. Some of it went into the vibrations that you could hear as it was rolling. It just gets all dispersed out. Okay? And there's no real good way to bookkeep it. So that's why we like these conservative forces, because they have a good bookkeeping system. Whereas these non-conservative forces, things get sort of lost. Okay. Any questions about this? So the way I actually like to use this equation when I'm solving problems is I say, because the mechanical energy is the sum of the kinetic plus the potential, usually I like to use it like this. Use like this. You say that the change in the kinetic energy plus the change in the potential energy is equal to the work done by the non-conservative force. That will just be the change in the mechanical energy. Okay. Any questions so far? We'll do an example so that it becomes clear. All right, so example, we'll do lots of things with sleds and sliding and inclined planes. So quiz 4, knowing friction is, I will include friction back into the review for quiz 4 because it sort of like plays a starring role in the last. So, and inclined planes. So let's say a sled. My what? Oh, okay. Thank you. Thank you. Thank you. Right. A sled. A moment there, I thought something was going to fall off the table, so I was trying to find it. All right. The sled slides from rest down a slope with angle 20 degrees from horizontal. Okay, here is the sled. Okay, it's going to look kind of like, okay, it's not such a great sled. There's a little person in there having fun. And this angle is 20 degrees. The sled is sliding like that. Okay, we have information, the coefficient of kinetic friction. Coefficient of kinetic friction is 0.050. Okay, not that big because it's slippery, icy slope. And how fast is it going? How fast is the sled going? How fast is the sled when it travels? Or after it travels, maybe is a better word. When it travels 100 meters down the slope, measured along the slope. Okay, so that's the problem. Sled slides from rest down a slope with an angle 20 degrees from horizontal. The coefficient of kinetic friction is 0.05. Okay, I'm missing the key word here. How fast is the sled when it travels 100 meters down the slope? Okay. Any questions about this? Okay, so let's take a look at this. All right, so before we do the problem, let's just try to organize in our head what can we do. We learn that the change in the kinetic energy plus the change in the potential energy, that gives me the change in the mechanical energy. And that should be the work done by the non-conservative force. Okay. So what is the non-conservative force in this problem? Friction. That's right. Okay, gravity is a conservative force, so that will be represented by the potential energy. So what I will need is I will need to know things like what is the work done by friction, okay? And then I will have to deal with the initial and the final kinetic energy, initial and final potential energy. So there's sort of like 5 steps involved here, right? It's going to take a little bit of effort. Right, everybody's clear on the mission here? It's going to take a little bit of time to do it. We're going to need the work done by friction. We're going to need the change of potential energy. We're going to need the change in the kinetic energy. And that hopefully will give us the final speed because it starts from rest. Does everybody see that path where we're going? Okay, so let's try this. Okay, let's, in my notes I start off with doing the kinetic energy and the potential energy. But let's do the force. Let's calculate the work done by friction first. Okay. So let's remind ourselves how friction is going here. We have this inclined plane, and then let's just draw it as a box so it's not too complicated. And then we have there's gravity going straight down like this. Okay, Fg. And remember we have this is 20 degrees because this is 20 degrees. All right, and then we have the normal force like this, Fn. And then we have the force of kinetic friction trying to oppose the sliding down the slope. Okay, everybody's with me on this? All right, so in order to figure out the force of kinetic friction, I need to know the normal force because then the normal force with the coefficient of kinetic friction will tell me the friction force, the kinetic friction force, okay? So let's look into the perpendicular direction here. So we're going to look in the perpendicular direction. Remember, so what is the perpendicular direction? This is the perpendicular direction. This is the perpendicular direction. All right? So we have Fn is going in the perpendicular direction. And then we have this component of force of gravity. So that will be minus Fg times, this angle is 20 degrees, so it's this component I want. So which trigonometric function do we know what I need here? Cosine 20 degrees. Okay, and what should that equal? 0, because what I'm doing is I'm saying this is equal to the mass times the acceleration in the perpendicular direction, but it's not accelerating in the perpendicular direction. It's not lifting off the surface. Okay? Everybody good on that? Okay, so this is equal to 0. All right, but Fg is just m times g. All right, and so now I can write down Fn is equal to m times g. All right, let's see. I don't have an m. In my notes, I just carry the g along with it as well. So let's just do the way I did it in class. I did in my lecture notes. So cosine of 20 is about 0.940. So this becomes 0.940 m times g. Okay. Yeah, you might say, why don't I just plug in 9.8 for my g? I could do that, but in my notes I didn't do that. So let's just leave the g alone. Okay. So everybody's okay with that? The m's will cancel out in the end. Okay, now let's calculate the force of kinetic friction. So I need to multiply the coefficient of kinetic friction, mu k, to the normal force. Okay, so that means 0.050 times 0.940 mg, and that comes out to 0.047 mg. Yes. I should have said 0.05. Maybe I said it wrong. It should have been 0.0. Yeah, I wrote it right. I may have said it wrong. Yeah, it's possible I said it wrong. All right, good. Okay, we're almost done with this problem. Well, no, actually, I lied. We're halfway done with this problem. Okay, so now we need to calculate the work done by friction. We got how big it is. Now we know it's going in this direction with 0.047 mg. Now we have a distance. How far? Does anybody remember how far we're going? 100 meters. Yeah. 100 meters. It's 100 meters. Okay. Yeah, 100 meters. Okay, it's a little unfortunate that the symbol for meters is m, and I have this m floating around here. So I'm going to leave off the units of meters so that it doesn't get us all confused. Okay? Is everybody okay with that? Okay, the m's are kind of going to get in the way. So then the work done by friction, that's what I call the work done by non-conservative forces. That's the only one we have here. Will be, okay, because I'm pointing in opposite directions, does everybody agree that it will have to have a negative sign? Okay. Because the angle is 180 degrees, you have the cosine of 180, that gives you -1. So then I multiply these together, and I get 100 times 0.047, and so that becomes minus 0.47 times mg. Okay. There's some units floating around here that I'm not dealing with, but that doesn't bother me if it doesn't bother you. Okay. Now, everybody good on that? So let's just put this away. That's the change. That's the work done by the non-conservative force. Now we need a change in the potential and the kinetic energy. So let's figure out what's going on initially. So initially, okay, thank you. Ki. What is the initial kinetic energy? Why is it 0? Because it's at rest. Okay, it's at rest, no velocity, no speed. Okay. Now, what is the initial potential energy? Well, that kind of depends on what you want to take as your reference height. Okay? Here's your choice. You have the slope. It's going down like this. You can take your reference height maybe as being the bottom, or you can take it as being the top. Which one do you prefer? Okay, all right. I wanted to take the top, but okay. Okay, let's take it to be the top. So now you're making me do different for my notes. That's okay. So let's take the bottom. So this will be y equals to 0. And now we have to figure out how high we are if this is 20 degrees. Okay? So this will be, to get the height here, that will be the sine of 20 times 100. Okay? And that will end up being 34.2 meters. Okay. The sine of 20 times 100. Okay, so then the potential energy for the initial case will be m times g times y initial. Y initial is 34.2 mg. Everybody's with me so far? Okay, so remember what we're doing here? Remember we're using the work done by the non-conservative force is equal to the change in the kinetic energy plus the change in the potential energy. We calculate the force of friction. It's a good review of how to get the force of kinetic friction. Okay? Normal force times UK. And then we calculated it went down 100 meters. Friction was going this way, and the distance, the displacement was exactly opposite to it by 100 meters. Multiply them together with the minus sign. And then we got that the work done by the non-conservative force is minus 4.7 times mg. Now we're getting the initial kinetic energy and the initial potential energy. And now let's figure out what we have in the final case. In the final case, K final, we don't know that because we are trying to figure out how fast it's going. V final. Okay, let's call it V final. This is 1/2 mv final squared. And then for u final, that's easy because we set y equals to 0 at the final point. Okay. So everybody's with me so far? Got it? Now we just need to pull it all together. So we have the equation that we're almost done. This time I'm telling the truth. WNC is equal to delta K plus delta U For WNC, we ended up getting minus 4.7 mg. For delta K, well, we can no, you can't quite see that, can you? No, you can't quite see that still. Okay, so Ki 0, K final is 1/2 mv squared, v final squared, so we have 1/2 mv final squared for the change in K. Okay. And then for the change of the potential energy, we have, this is the final, and this is the initial, this is the initial, and so we end up with minus 34.2 mg. Okay, so everybody's with me so far? I know this is not the most exciting thing, but are you following the steps as we go along? Okay, we're almost done. So now we bring these to the same side, and we have 29.5 mg is equal to 1/2 mv squared, v final squared, and then multiply by 2, get rid of your m's, and finally stick in g, finally, and then we have v final squared is equal to g times 2 times 29.5, which is 59 times, why did I do it in this order? I don't know why I didn't do it this way. M times g, okay? Oh, I canceled the m's already, thank you. That was a meters, that was in my notes. Thank you very much. Okay, and then there was a meters, there's a meters floating around here to get the units right. That I was dropping, by the way. That was, okay. Is everybody okay with that? I dropped the meters along the way because it looked like an M. I put it in here, but you caught me on that I shouldn't write it as an M. There's a meters hiding in here, otherwise the units don't work out right. Okay, so now then we take the square root of both sides and we get V final is equal to 24 meters per second. You plug in G is equal to 9.8 meters per second squared. Then we have another meters here. You get 59 times 9.8 meters squared per second squared, take the square root, and you end up with 24 meters per second. Okay? Any questions about that? Other than that was a long problem. Okay, so now let's try to do something more conceptual so that you get a feeling for this without quite so many details. So let me do a summary in pictures. Okay, so we did this thing called the work energy principle or work energy theorem. And the way I like to think about it is I have this thing, kinetic energy. Remember, I think of that as the cash on hand. And I think about how much money I have and the work done by all the forces, including the conservative and the non-conservative forces. So I will have an exchange of money or energy. Then I have here the W net. This is due to all forces. Okay? So the point is that if some force does some work on me, that they're giving me money, they're putting cash in my pocket. So that means that the change in the kinetic energy is the work done by all the forces put together. Okay. Does that make sense, what the picture is saying here? If you add up all the work done by all the forces, then that will be the change in the kinetic energy. Now, if I do the conservation of mechanical energy, the simple version, where I have an isolated system and I have kinetic and I have potential. I kind of do this before, and this thing is isolated. Then I have some exchange of energy or exchange of money between kinetic and potential. And the point is that whatever change in kinetic energy plus the change in potential energy has to be zero. Okay? The sum of both of them together, the whole unit, that can't change the total. So I would write K initial plus U initial is equal to K final plus U final. Does that make sense, everybody? Okay. And now this new wrinkle with the non-conservative forces with like friction. So with non-conservative forces, in that case, it looks more like this. We have kinetic, we have potential, okay? And so there can be energy or money exchange between the two, but then we can have other things playing a role. We can have exchange of exchange of energy with other forces, W and C. So these are the non-conservative. But the way I like to think of it, if I think about the kinetic and potential energies put together, then whatever is done by the non-conservative force will give you the change in the total mechanical energy. So the change in the total mechanical energy, the sum of all this stuff, the change in those guys added together, would be the work done by the non-conservative force. Okay? Or as I've written it, delta K plus delta U is equal to W and C. Okay. Any questions about that? Yeah, so your book, I read through that section, and I thought, that was kind of, they have these bar charts of potential energy, kinetic energy, and the non-conservative force and all that stuff. And there's one problem in your homework on this. I have to admit, I've never seen that before. So in my point of view, those bar things are not, they're kind of cute and interesting, but not that important. Yeah, if you find the discussion in the textbook a little bit confusing, hopefully what I presented here is pretty straightforward. Okay, that's all you need to know. All right, let's do a quick question. Okay. So a 1.5 kilogram block is released from height h equals 0.3 meters and slides down a frictionless slope. It runs into a spring, an elastic spring with spring constant uh, 3,550 newtons per meters. And the question is, what is the maximum compression of the spring? Okay, and let's see. A, B, 2.04 centimeters, 4.54 centimeters, 6.63 centimeters, 4.98 centimeters, 9.72 centimeters. Okay, I will open up the polling now. I'll give you another minute to work through it. Okay, if you haven't already made a choice, go ahead and make your best choice now. And we'll go over the answers. All right, everybody had a chance? Ready? Everybody? Go ahead. Okay, I'm going to close it. Okay, so yeah, this is a little bit more difficult problem. Let's take a look. Okay, we're doing conservation of energy. So let's figure out what's going on initially. Initially, mass starts from rest. There's no kinetic energy. Okay. Now the potential energy will just be due to the gravitational potential energy from let's say at the bottom it's height 0, so mgy so we have 1.5 is the height is the mass, 9.8 is the gravitational, well, it's g, and the height is 0.3, and that comes out to 4.41. Then for the final case, okay, now maybe it wasn't obvious when it's at maximum compression, the object is momentarily at rest, okay? And so that means the K final is equal to 0, again. And then the U final, though, is now because at the bottom there's no potential energy for gravity, because we'll set y equal to 0 at the bottom, okay? So then we'll have mgy final, that's equal to 0. But we have the spring potential energy, that's 1/2 k x final squared. And we know what the spring constant is. It's 3,550. So we have 3,550 times x final squared. Then we say that k final plus u final is equal to k initial plus u initial. And so we have that 1/2 3,550 times x final squared is equal to 4.41. And so you solve for x final, and you get 4.98 times 10 to the minus 2 meters, or 4.98 centimeters. Okay. Any questions? If not, I'll see you guys tomorrow.
That's the way to go. That's another. They just took it for like just for safety.
I didn't know what I was going to minor in. And so,
Yeah. So, yeah, I recommend the way I did it. There's a minus sign here that I was wondering why. Well,